Let's look now at moving from equations involving absolute values to inequalities with absolute values. We can actually carry a lot of the same techniques over with us because for the CLEP, we focus on a very specific form of absolute value inequalities. We look at ones involving first-order polynomials. So they look something like this. I have absolute value ax plus b. And before I would say this was equal to some constant c. Now I'm going to say it's less than or equal to c, or perhaps greater than or equal to c. Which one it is isn't particularly important, because our technique works equally well for both of them. So let's look at a method called the number line method. This is a fast, efficient way to solve these types of problems. The first step is to solve with the corresponding equation. So what we did in the previous section. So we solve absolute value ax plus b is equal to c. So again, in general, we'll have two solutions for this. Once I find those, I will plot them on a number line. And then our final step is to pick points in the regions defined after plotting my solutions and check whether they satisfy the inequality or not. And that will determine if the corresponding region is part of the solution space or not. So I check points in the regions on the number line. So let's look at an example of this. Absolute value of x minus 7 should be greater than or equal to 4. So what we'll do to solve this is start by solving the corresponding equation. We'll look at absolute value x minus 7 is equal to 4. So I know this has two solutions. I know x minus 7 equals 4 as a solution, and x minus 7 equals negative 4 is also a solution. So this gives me x is equal to 11, and this gives me x is equal to 3. So what my next step is, and this is different from just solving the equations, I'm going to plot these on a number line. So 3 is here, and 11 is here. And now I'll pick points in the regions to check where I'm a solution. So from this region, a nice point to use is x equals 0. Here, let's take x equals 10. And here we can take x equals 20. These are just simple numbers from each region. So for x equals 0, I plug it into my original inequality and see if it is satisfied or not. So I have 0 minus 7 should be greater than or equal to 4. Well, thankfully it is. This is the same as saying 7 is greater than or equal to 4, so it's good. So this is a region that satisfies the inequality. Everything that is less than 3 will satisfy it. Now we'll look at the choice of 10. So absolute value of 10 minus 7, we're asking, is it greater than or equal to 4? Alas, it is not, because this is saying is 3 greater than or equal to 4, and the answer is no. So everything in this region fails to satisfy the inequality. So these are non-solutions. So nothing from 3 to 11 works. And then we'll check 11 and greater. So let's take 20. Absolute value 20 minus 7. Is it greater than or equal to 4? The answer is yes. This is the same as asking is 13 greater than or equal to 4, and it is. So this is also a solution. So what this tells me is that anything that's less than or equal to 3 or greater than or equal to 11 is a solution. So I conclude that from minus infinity to 3 is a solution, and so is everything from 11 to infinity. Everything in between fails to satisfy the inequality. Let's look at another one. Let's look at absolute value of 6x minus 1 is less than or equal to 2. We'll play the same game. I'll start by solving the equation. So I solve these separately. So this tells me that 6x is 3, so x should be 1/2. Here this tells me that 6x should be equal to minus 1, so x is equal to minus 6, 1/6. So my number line looks like this. And again, I'll check points from each region. Let's take x equals minus 1 here, x equals 0 here, and x equals 1 here. And we'll plug into the inequality and see if it holds or not. So for x equals minus 1, I have to check is minus 6 minus 1 less than or equal to 2 in absolute value. Well, that's the same as saying is 7 less than or equal to 2, and the answer is no. 0, does it work? Well, is 6 times 0 minus 1 less than or equal to 2? That's only if 1 is less than or equal to 2, and it is. So everything in here works. And then I take x equals 1. 6 times 1 minus 1 less than or equal to 2. That's if and only if 5 is less than or equal to 2, which it's not. So nothing in here works. So this is different than the previous example, where the region in the middle failed, but the regions on the outside worked. Here it's opposite. The region in the middle works, the region on the outsides fail. So what is our conclusion? My solutions space is minus 1/6 to 1/2, and nothing more. Note that I include the endpoints, minus 1/6 and 1/2, because if I plug those in, I get equality. I get equals 2, and that's okay. I'll say this as a remark. If I don't have less than or equal to, if I just have less than, I use open parentheses, not closed parentheses. So a small point, but one that may come up on the CLEP exam.